It's working. You see green on the top. Working. Is my mic working? Is my mic working? I think it's working fine. Still works. It's 49, so we'll start in a minute. Right? It's in. So let's get started with today's concept live stream. Today we're talking about 1.65. We're looking at definite integrals. The agenda of what we're doing today is to have an lecture as always. Then we're going to talk a little bit about rules of integrals, and we're going to do a bunch of practice definite integrals. And then there might be a little bit and to ask any questions. And as always, if after the session you want more help one-to-one, you can tutoring.asu.edu, and you can get one-on-one help tutor by going to that website, go to our center, some more information about the end of the session. Thank you for this Math 265 concept session. This session is being recorded, keep that in mind, and will be made available for you all approximately before the session ends. Should be able to find the tutoring website, receive an email about it, I think. And also, please be respectful in the session, and I do encourage you to use Zoom chat, interact with me, and answer questions or comments on math we're doing. That improves the quality of the session. You guys interact with. That's it. To some content. Now then, let's take a look. So first, we're going to practice a little bit of rules of integration. So in this first column, it says knowing that, and it tells us the integral of some function f of x from 4 to 7 is equal to 10. The integral from 12 to 7 is equal to 4. The integral from 4 to 1 is equal to -3. And knowing all these three properties of f of x, it wants us to find the integral from 12 of the same function for x, right? So we're talking about rules of integration. I guess it might be more right to like properties of integration, so to speak. But what I'm trying to get at with this problem is if we have an integral from 1 to 2, integral from 2 to 4, how can we combine them to find an integral from 1 to 4, so on. So I'm gonna kind of write the rule over here, and I'll use placeholders a and b, where a is less, but a is less than b is less than c of some f of x dx plus the integral from b to c of some f of x dx, for example, is equal to the integral from a to c for some f of x dx, right? So that's like one property we know of. And another property, knowing that a is less than b is less than c, is that the integral from b to a of f of x dx is actually equal to the opposite, or the negative, of the integral from a to b of f of x dx. So how can we use these two properties to help us find the integral from 1 to 12 of f of x or dx? Well, we want to write everything in term from like low to high, so to speak. So for ones like this one and this one, we should rewrite them. So we can write the integral from 7 to 12 of f of x dx is going to be the opposite of this one, right? Write it as negative. The integral from 1 to 4 from f of x dx is going to be negative 3, which is just 3. Wait. So then, now we can use this one and the other one that we have to say that the integral 1 to 12 of f of x dx is going to be the integral from 1 to 4 plus, and then just being a little lazy there, I can write out the notation. F of x dx is the integral from 4 to 7 of f of x dx plus the integral from 7 to 12 dx. So then we know what all these are equal to, so we can just plug in, we know. So from 1 to 4, we have 3 plus negative 4, oh wait, not negative, plus 10 plus negative 4. And we can write it as 3 plus 10 is 13. So it's equal to 9. The integral from 1 to 12 of f of x dx is equal to 9. And we did that by using the properties of integrals, such as integrals for a interval. So if there's any questions on that, just let me know and go over it again. If not, I can go on. I'll just leave that up. 2 seconds. Take a look. However, it's recorded. Keep that in mind. Sessions. Now we can do some more practice or some actual practice integration. Now we have a function and some bounds and we're going to integrate. And so what's the difference for you guys between integrating without bounds versus integrating with bounds? What's going to be the difference that we do? Let's say that we're integrating some f of x, dx. So without bounds, we're going to get a answer the antiderivative of f of x, right? Big F. And then we write plus c, right? But with the definite integral, we get that big f of x, and then we draw that line, and we kind of take it at b, and we're gonna like evaluate it at a and at b. And when we do this notation, it's gonna be f of b minus big F of a. So, and then when I write the big F, that's just notation like the antiderivative, because when we take an integral, we do an antiderivative, and then we evaluate at the bounds, or we add a constant in case of it being an undefinite integral. So that's kind of the process, or at least the differences process. So then let's take these derivatives. So let's start with this one. Part A, integral from pi. And so you can kind of ignore the bounds for the most part while we're first starting out. And then once we have the actual antiderivative, then we can bring it back in. So I'm just going to rewrite it so we can solve it. So then we'll be the integral of cosine of x. Remember, when it comes to these separate terms, we can take it as the integral of this one minus the integral of this one. Just like when we're doing derivatives, we can split them up. We can bring constants out if we want to. Write it as -2 sine of whatever, because the constant can affect it really in the same way. Bring it out, it's constant. So then what would be the integral of cosine of x? Okay, writing. If integrals kind of confuse you with the notion, just think of it as doing the opposite of a derivative. What do I take the derivative of to get a cosine? Well, if I take a derivative of sine, for example, I get cosine. So then the integral of cosine gets back to sine. I do need a x, getting that. And then we're going to do a similar thing over here. So I'm actually going to keep the negative in, and you'll see why right now. So how do we get a negative sine of x? Or never mind, I wrote that wrong. It's if we have a negative sign, what do we take the derivative of to get a negative sign? What do we take if we take the integral of negative sign, what do we get? And another way to think of it is, what do we take the derivative of to get a negative sign? Well, if we take a derivative of cosine, we get negative sign, right? So that's why the integral of negative sign is cosine. Because if I have cosine of x and I take that derivative, I end up with a negative sign. So that's why in this case it was good to leave the negative in. But like if I didn't leave the negative in, right? In order to get a positive sign, I would have to take the integral. I would have to, in order to get a positive sign, I would have to take the derivative of a negative cosine, right? That would give us a negative sign. It would make it positive. And then when we get that, we just have a double negative sine of x plus 2 cosine of x. And so we took the antiderivative, but am I done yet? What am I missing? Yeah, we got to take the bounds, right? We can't just leave it like that because this is just the antiderivative. This isn't even the integral. If it was the integral, we would have a plus c. So, but right now we have bounds, so we have to take it. We have to evaluate it between 0 and pi, right? So we do sine of pi plus 2 cosine of pi minus. I put the big parentheses to remind me that it's minus everything. Sine of 0, 0, and 0. So then you have your sine and cosine of pi memorized. It's easy. If not, you just put in your calculator. Check. Make sure you're radians. So in case you remember, sine of pi is 0 plus 2 cosine of pi is 1 minus sine of 0 is also 0 plus 2 cosine of pi. Cosine of is actually negative 1. So then we can type that at 2 negative plus 2 is 4. So then after all that work, we found that a integral from 0 to pi of cosine x minus 2 sine of x is equivalent. Anyways, so yeah, that was what we did. I'm gonna erase this right here so there's room for part B. Switch colors to distinguish. I'll do part B in green. So it's a pretty similar process to the last one, where doing an antiderivative, then evaluating a bound specified problem. And so when it's this, we kind of do an inverse product rule, right? Where if it's a derivative of x to the n, we get a n x to the n minus 1. So if we're taking an integral of x to the n, we divide by n, divided as n to the x plus 1. My bad. Anyways, so let's look at this one and take the integral. Yeah. Anyways, let's take the integrals. So I can just leave the integral sign out here. Actually, once we integrate, we don't need the integral sign. So if we just integrate this all in one run, so it's going to be x to the fourth, and then we divide by 4. It's 1/2 x to the fourth. And the way to double check that this integral is correct is we can just take the derivative of this right here, end up with 4/2 x to the third, which is 2x squared. I mean 2x cubed. But we know that we did that one right. If we took the derivative, it could be the same as what we started with. So that's a good way to make sure. Like, I was a little unsure of this. I don't know why. I thought I might have wrote it wrong, but we add 1 to the exponent and divide by that new exponent, and then we have minus x to the fifth, 3 divided by 5, plus 3 x to the first. We can divide by 1, divide by 1. It's the same as doing nothing. And then we can write that line and go from the 3, and then it's this part's a little longer, but plug in everything, so it'd be 1/2 3 to the fourth minus 3/5 3 to the fifth plus 3 3 minus big parentheses small like 1/2 1. And the only reason I'm not writing the exponent is because it's 1 to any exponent is 1. 3/5 1 is 3 times 1. So then you could just put this into your calculator and get a value. I can do that now. You guys want? 1/2 3/5 5 3. The answer is 99 negative. Negative. So that's the integral. You guys are hearing me good? And the green Zoom mic light up. All right, that's fun. Got some more examples to work on. Let's do it. Do part C right here. Green. And so this one's pretty similar to the first one, except now it's 3x times up. In order to make this easier for us, what should we do first before taking this in? Any ideas in chat? You guys? Yeah, we can actually distribute this first and make it into a or to like a polynomial, right? So we have 6x cubed minus 12/6. I can write that as 2 x fifth minus 9x dx. Then we can say that this is equal to 6/4 x to the 4 minus x to the 6 third, 2/6 minus 9/2 squared, evaluated -1/4, and then we would plug in x for 4, and then plug in x for 1, and it's 1, so 6 over 4, 4, it's 1/3, 6, minus 9 over 2 squared, minus, big parentheses, 6 over 4, negative 4th, 1/3, negative 6, minus negative 1 squared. And I'm going to leave that one there. The rest of it is just putting in your calculator. To save a little time. Let's look at part. Let's do center red right here. E to the x minus secant squared x is 3x x. So for e to the x, if you remember the rule, the derivative of e to the x is just e to the x. Then it's kind of the same case where the integral of e to the x is just e to the x. So don't get too worked up with e to the x. You bring it down again. Minus. And the integral of secant squared of x, this is one that's good to kind of have memorized. If you can memorize at least the derivative of sine, tangent, but have a hint of what this is. In case you don't know, what is the derivative tangent of x again? Yeah, it's actually secant squared x. So that means that the integral of secant squared x is just tangent of x. And then 3x, so we just do the same rule. X squared 2. So double check that. Derivative of 2x squared, derivative of that is equal to 3x first. It's all good. That's all good. And then we evaluate from 0 to pi. And one more thing. So I know I said like listing individual ones is how we double check to make sure that our integral is correct. The same way as like if you want to make sure the overall whole thing is the correct antiderivative, you would just take the derivative of e to the x minus tangent of x plus 3/2 x squared, and just double check that that's the same as e to the, and that derivative would be the same as e to the x minus secant squared x plus 3x. Then we can plug in our bounds and evaluate e to the pi minus tangent pi 3/2 squared minus e to the 0 minus tangent 3/2 squared. And let's evaluate this right. And then pretty sure tangent pi is 0. Yeah. Minus 0. We have pi squared. Don't forget pi numbers. Concerned when you see that getting squared, cubed or something. Just treat it like not a 1. 3 minus 1 plus, and then tangent 0. So I double check 0 minus 0. And that simplifies to e to the pi plus 3/2 pi squared minus 1. That would be our answer. We could plug it into our calculator and get a decimal, but that right there is technically more correct because worry about in decimals is number, So you could leave it there. But yeah, that was how we took the integral of the x minus secant squared x plus 3x from 0 to pi. Let me know if there's any questions. This is being recorded. Website is tutoring.asu.edu. One-on-one. I do have your sample week. Okay. So this is more of a word. Tells us that You're driving a car down a road and your velocity can be modeled by the function f of x. Find the distance traveled after 4 hours of driving. So if we're taking the distance traveled after 4 hours of driving, what do we have to do this function? I mean, as a hint, you guys can already tell we're gonna take an integral. Otherwise, I would be asking it, but there's a relationship between acceleration, distance, and velocity. Usually we have acceleration as a of x, velocity as v of x, and then we use distance like s of x, sometimes v of x, sometimes see s2 for some reason. Why? I don't really know either. Just kind of do it. But you may remember that s of x prime equals v of x, and v of x prime a of x. Well, there's another relationship with integrals, and you might be able to tell what it is already, but it's integral of a of x equals v of x, and integral of v of x equals s of x. So if this is our function, which is for velocity, where in this case we can say v of x equals f of x, to get the distance traveled, we're just gonna have to take the integral of f of x, right? So the integral of x squared minus 6x plus 9, x will help get us a s of x function. But how can we make the bounds for this one to help us solve it quicker? If we want to know the distance traveled after 4 hours of driving, how should we bound this integral? Yeah, so if we want the first 4 hours, we can just go from 0 to 4, assuming that this function is in x hours, of course. It's not specified, but I think based on the way it's written, it's kind of what the alpha column meant. Okay, but anyways, so we can take the integral from 0 to 4 of this. So we have 1/3 x cubed minus 6 over 2 squared is 3 plus 9x 4. We have 1/3 4/3 is 3 4 squared is 9 4 minus we have 0 minus 0 0, put zeros 0, put that in our calculator. Third, 3 third, so 5 3 miles. And you might think like, oh, why do I have to do bounded integral? Couldn't I just done like s of 4 or something? And in this case, it would have worked out. But what if at 0 we already have some amount of distance already covered? You know, like that's why we have to evaluate from 0 to 4. Like what if s of 0, for example, was like 10, then it would have been 105 minus 10, and just taking e of 4 wouldn't work. That's why you have to make sure you take the integral. And yeah, so just keep that in mind. And those are all the examples I had for today. Just know we do these concept sessions every week. And I think next week, Thanksgiving, I'll have one. And then we have review sessions starting next Monday on 11/23 for exam 3. So now on the tutoring website. And again, the tutoring website is tutoring.aesu.edu. That's where you get one of the tutors, see the schedule, get links to the sessions and recordings. So I highly recommend going there when you have a chance. Tutoring is open right now. As a matter of fact, today Mondays through Thursdays, we're open from 8 a.m. to 11 p.m. Fridays from 8 to 3, and Sundays from noon to 11. So, practice. Thank you for joining me today, and hopefully this recording will feature classes and with finals soon. Have a nice night. Thank you so much.